Hey everyone, it's Canfield, Mr. Canfield, the only Canfield that teaches AP Calculus at Conrad Schools of Science. Okay, anyway, I am going to go through the homework so that anybody who needed extra help can get it. So I got to go pretty quickly, but I will try to speak clearly. Well, let's just get into it. All right. A hot air balloon. Did I say what this is? This is related rates homework. A hot air balloon rising straight up from a level field. Okay, so that's telling us the balloon is going straight up. Okay, so that already tells us this does not change here, but the other two are going to change. Because if we think about it, as it's moving, that line segment's going to be getting longer, and then from here to here, that's going to have to be getting longer too, but that's going to stay still. So it's tracked by a rangefinder 500 feet from the liftoff point. So this is 500 and it's not changing. At the moment that the rangefinder's elevation angle is 45 degrees, the angle is increasing, so d theta dt is 9 degrees. So how fast is the balloon rising at that time? Well, if this is, I can call this my height, right? And I can call this A, B, and C, just like we normally do. But we're not going to need any of that because there is a trig ratio that deals with the far side and the close side when we're dealing with an angle, opposite over adjacent. We can say tangent of, now this angle is changing, so I need to call this theta actually. Tangent theta is equal to h, which is changing, over 500. And it wants to know how fast the balloon is rising. So it wants dh dt. So since we want dh dt, I want to make sure I include h in my formula. That's why we're not using our hypotenuse here. That's why I knew to use h. Well, so let's see what happens if we take this derivative. But before I do that, I'm going to remind you that this is tangent of theta is equal to 1 over 500 h. Those are equivalent statements. So the derivative, well, the right-hand side's the easy part this time. It's 1 over 500 dh dt. And the left-hand side is going to be, well, the derivative of tangent is secant squared, so secant squared theta. And then we took the derivative of a theta thingy, so it's d theta dt. And the thing is, we know d theta dt, it's 9. And we know the angle that we care about. It's 45. So I'm just going to remind you, let's see, if I wanted to find secant squared of 45 degrees, this is the same of 1 over cosine of 45 quantity squared. So cosine of 45 degrees, 45 is pi over 4, so that means that if we're dealing with a pi over 4, that's a 1, 1 squared of 2 triangle. So cosine of 45 is adjacent over hypotenuse. So cosine of 45 is 1 over the square root of 2. So it's going to be 1 over the square root of 2 squared. That's kind of a silly way to write it though, because 1 over is just the same thing as flip the flip. It's back to normal. So now I can say this is just the square root of 2 squared. I am so sorry. A professional video editor would edit that out. Yep, I'm not that. Square root of 2 squared is, I was going to say 4, but that'd be the square root of 4. So that's just going to be 2. So this is going to be 2 times 9 degrees is equal to 1 over 500 dh dt. So multiply both sides by 500, then we'll get, whatever that is. 1,000, 9,000? 9,000 feet per minute. My assumption here is that Oh, I'm so sorry. My assumption here is that if there's some problem with us just using 9 for the angle. He might want us to change it to radians or something. But I care more about like our general process and the calculus than unit conversions and consistency there. Let's see. If the balloon rises at 100 feet per minute when the angle of elevation is 45 degrees, how fast is the angle changing? So instead, we could be here, secant squared theta d theta dt equals 1 over 500. But this time we know we know dH dt, so we're able to go in there and put the 100 there. So how fast is the angle changing? It's just saying angle changing is d theta dt. Okay. I'm realizing I keep on leaving out important details about how I know which thing is which. On the next problem, I'm going to do better. So I got 2 here, so we'll divide both sides by 2. I got 50 over 500. I got 1/10, so that's gonna be 1/10. That might be radians per minute, since it doesn't already have. It might be degrees, because once you take a secant of something, you just get a number. It doesn't deal with radians or degrees anymore. It's just a number. Okay, here we go. So water is poured from a dispenser into a paper conical, so conical, that means cone, and they show you the picture over here, so that's helpful, cup at a rate of 2 centimeters cubed per second. Centimeters cubed, that tells me volume. So 2 then, that has to be dV dt. So that's telling me I'm going to want to use the volume equation. The cup has a height of 15 centimeters and a top radius of 5 centimeters. So like this is 5 and this is 15. Radius was 5, height was 15. Find the rates that the water level is rising. Water level rising. Okay, so out of our different terms here, we've got volume, we've got height, and we've got radius. Well, water level rising is going to be height, and it's a rate that the water level rising. So that's going to be dH dt. When the water is first 2 centimeters high, and I think I said to get rid of the rest of that, we really just care when it's 2 centimeters high. It's an interesting problem to do the rest, but we're more concerned about going through this process and doing the calculus and getting answers. And so anyway, so using our volume formula, volume is equal to 1/3 pi r squared h. So using that, if I want to find dH dt, then that means that over here, I want to make it so that I can take a derivative and only have the letter h over here on the right-hand side. So to do that, I'm going to have to make some sort of similar triangles, and the diagram is actually set up to really help us here. So the total height of the cone is here, the total radius of the cone is here. And so that's a 5 and that's a 15. And so when we're doing these similar triangles, we can say there's the big triangle and then the little triangle inside of it. So the big triangle has a 5 and a 15. So I could do 5. Now that was the radius of my big. So my small one, we don't necessarily know the radius at any given point in time. So we want to generalize it and say 5 goes to r. 5 compared to any smaller radius of this cone is the same as the total height, 15, compared to any smaller height based on the water level. This isn't the only way to set it up. I set it up differently in class, and I'm doing that on purpose. I want you to see different ways to do it. So either way, my goal here is to make it so that I can eliminate r over here and just have h's. So I'm going to solve this for r by first multiplying both sides by the denominators and getting 5h is equal to 15r. And I'll divide both sides by 15. So 5 over 15 is 1/3, so I'll say 1/3 h is equal to r. And so now we'll go over here. Because I really want to make sure I explain that, well, how did you know to eliminate that letter instead of that letter? If it had said, how fast is the radius changing, then we would go in here and we'd make it so that we can get rid of the letters that aren't radius. So we'd get rid of H. All right, so I'm going to put a 1/3 H and where R used to be, sorry. So now when I square it, 1/3 pi, this is a 1/3 H times a 1/3 H, so a 1/3 times a 1/3 is a 1/9. H times H is H squared. The H comes down. So then 1/3 pi and 1/9, I could write that as pi over 3 times 9 is 27. H squared times H is H cubed. And that's volume. We have not taken the derivative yet. On our next step, we'll take the derivative, and I get dv dt is equal to 3 pi over 27 H squared. Is that fair? We take 3, multiply it by that number, decrease the exponent by 1, and then we multiply by the derivative of the inside of that H, which is dH dt. The question asks us, find the rates that the water level is rising. Well, okay, let's dH dt. So I'm going to take whatever dV dt is, I'm going to take that and divide it by all this mess. Which another way to do that is to take dV dt times the reciprocal of the fraction. So instead of writing 3 pi over 27, I wrote 27 over 3 pi. Wait, hold on. Instead of writing 3 pi over 27, those are both divisible by 3. So let's change it to pi over 9. Divide them both by 3, we get pi over 9. So now it's 9 over pi. And we'll divide by the h squared. So you can even put the h squared on the bottom there then. So dV dt times 9 over pi h squared, and that'll be equal to dH dt. So this is beneficial to do this. Sometimes they'll even leave their answers without plugging the numbers in. So dV dt was 2. So this is nice that I labeled everything, so now, oh, it's off screen. I labeled everything, so now I don't have to go back and read anything. Just find dV dt, then 9 pi, and h, did not write h. 2 centimeters high. Oh, hey, 2 times 9 over pi times 2, the 2's cancel. So I'm getting 9 over pi, and I see centimeters in the problem, so centimeters per second. So we modified that question for our class. But yeah, there we go. A cylindrical paint can. Now that's a cylinder. And I changed it for our class. Changed it to volume dt. Change in volume over time when the height of the paint is, I can't remember. Was it 3? Whatever it is, whatever number I told you to plug in, we'll plug in that number later. Anyway. Cylindrical paint can has a 6.5 inch inside diameter. Well, okay, the diameter is 6.5, so what's the radius then? Well, if the whole thing is 6.5, then we'll divide that by 2 to get the radius, so 3.25. 7.75 inches high, okay. Here's the difference from this to the previous question. In cones, when water fills up or drains out, the radius changes. If you can kind of imagine that going up and down, the radius is going to grow and shrink as the height grows and shrinks. In this, the radius is static. It doesn't change the entire way. So in a problem like this, if we're looking for change in volume, well, we know that volume is equal to pi r squared h, which is the area of that flat circle on the bottom times the height that it is. So The difference is the radius, the 3.25, does not change. So I can say volume is equal to pi times 3.25 squared h. So then when we take the derivative of this, we'll get dv dt is equal to pi times 3.25 squared, because this is just a number, times dh dt. And we know, hey, we don't even need to know what the height is. Oh, I'm silly. When I changed the question, I made an oopsie. I'll change it to how fast is the height changing? Because they told us the volume is coming in at 120 inches cubed per minute. So this is going to be 120 over here, and then we'll have our pi, we'll have our 3.25 squared, and then we'll have our dh dt. So we'll get some number here, we'll take 120 divided by it, and that'll be our answer. Silly me. I should have just had you guys skip that question, or do it the real way. Okay.